So I'm going to finish up the second part of the 10.4b notes with you. You'll notice this stuff we're talking about slope and tangent lines. So you'll notice a little bit here kind of mirroring our parametric equations stuff. It's going to look different, and I'm going to say what's we're going to write down is going to look scary. And in fact, I wouldn't necessarily go as far as to say to memorize what you're about to see, but kind of understand the point of what we're doing and then just take a derivative as you know how to. So what's going to happen here is that we're going to be using this idea that x and y can be written in polar function, or in polar, using our formulas x equals r cosine theta and y equals r sine theta. And we can think about these as some function of theta times cosine and sine of theta. So like, for instance, if r was equal to 3 sine theta, then our x would be equal to 3 sine theta times cosine theta. So we will be able to create functions for x and y as functions of theta. So if you're looking at this function of theta times cosine theta, and I were to ask you to take the derivative of x with respect to theta, I'm hoping you recognize that this would be product rule, because it is a product of some function f and cosine. So using product rule, the first times the derivative of the second, that's negative sine, so I'll throw the negative in front of there, plus the derivative of the first times the second. So if you want to do some memorization, dx d theta is going to be negative f of theta sine theta plus f prime of theta cosine theta. Similarly for y, if we're using product rule, first times the derivative of the second plus derivative of the first times the second. And as we were doing with parametric equations, when you're asked about tangent lines or the slope of tangent lines, we're really thinking dy dx. So if you do not have a function of x and y, we're going to have to take our derivative with respect to a different variable, in this case theta. So very, very similarly to parametrics, our dy dx is going to be dy d theta over dx d theta. And if we are substituting in the little formulas up above, we get f of theta cosine theta plus f prime theta sine theta divided by negative f of theta sine theta plus f prime theta cosine theta. This looks way harder than I think it's going to be, and I think it's going to be easier to take these derivatives. You just have to remember how to rewrite x and y appropriately using these r's that are not just necessarily going to be numbers or r's, they're going to be functions of theta. So we're doing everything through theta, no r's. All right, so similarly to our parametric stuff, if dy d theta equals 0, we are going to have a horizontal tangent. If you think about that, that would say that our dy dx equals 0. So that would give us our lines with 0 slope. And if dx d theta equals 0, is going to give us our vertical tangent. And if you think about that in our dy dx, that means the denominator is equal to 0, which means we have undefined slope for our tangent line. And then finally, if both are equal to 0, we can't tell. So keep that in mind. Because what is 0 over 0? Indeterminate. All right, an interesting thing that we need to know for polar functions, tangents at the pole, the zeros of r equals f of theta can be used to find the tangent lines at the pole. So an example. Find the equations of the tangent lines at the pole for 3 cosine 2 theta. This is a rose. This rose has 4 petals. And what we do anytime we're seeing a question asking for tangent lines at the pole, we need to find the zeros. So if I make r equal to 0, we're going to solve this equation. 0 equals 3 cosine 2 theta. We divide by 3. I'm going to flip sides here. We get cosine of 2 theta equals 0. And that means our angles 2 theta are going to be equal to those angles that make cosine 0. And if we're only concentrating on the angles between 0 and 2 pi, that's going to be pi over 2 and 3 pi over 2. And to get theta by itself, we have to divide everything by 2. So we get theta equals pi over 4 and 3 pi over 4. Let's take a look at what this kind of looks like in a sketch. So our 3 cosine 2 theta, believe it looks something like that. I think I drew it in the right order. So the way that I drew it around, I believe, is the direction that those curves go. But what we're talking about, tangents at the pole, you will see that we have a tangent line that only will cross through that graph at the pole right there. And that is actually our angle, theta equals pi over 4. And then we have one this other way, that way. And you'll notice that only touches the graph right at the pole. And that is theta equals 3 pi over 4. So if you're asked for the tangent lines at the pole for a polar function, you need to find the zeros. All right, last but not least, an example down here. Find the ordered pairs where the graph has a horizontal and vertical tangents. So thinking about what we have written up above, well, let's say we're starting with r equals cosine theta. So if we want the location, the ordered pairs, where the graph has a horizontal tangent, that is going to be when dy d theta equals 0. So we need to get dy d theta. Here's what you always have to start with these. We're going to start with y, and we need to do y is equal to r sine theta. From this, you need to replace r with a function of theta. We're using r equals cosine theta, so guess what, folks? We're taking that, and that is going to be our r. So y, in this case, is actually cosine theta times sine theta. Now, having written it like this, instead of having to memorize all this stuff that I wrote up above, just take the derivative of this with respect to theta. dy d theta equals, we're going to need product rule because it is a product of cosine and sine of theta. So that is going to be first times the derivative of the second. So that's negative cosine theta times cosine theta plus the derivative of, oh, I did that wrong. I'm so sorry. Let's start that guy over. If we start with the first, the derivative of sine is cosine. Sorry about that. So that's cosine times cosine. Plus, if we take the derivative of the first right there, that is negative sine times sine theta, or that is equal to cosine squared theta minus sine squared theta. You might recognize this. We do have a formula for this. I did kind of ask you to remember these, maybe not this one in particular, but you might recall that that is cosine of 2 theta. Why am I turning it into that? Because we're trying to find where this equals 0. And writing it in that way, that's going to be easiest, in my opinion, to find where our zeros are going to be located. So we're actually going to take our cosine of 2 theta, set that equal to 0. Kind of did that up above if you want to take a look. So that is going to be when theta equals pi over 4 and 3 pi over 4. Now, we do need some ordered pairs, r theta or x comma y here, because the question asked for the ordered pairs where this was happening, not just necessarily the angle. Let's just plug these into, let's get some x and y's. No, just kidding. Let's do our r and theta. That'll be the easiest. We have theta. So how do we get r? Well, r is equal to cosine theta. So if we plug in pi over 4, so r, when we have cosine of pi over 4, is equal to root 2 over 2. So one of those ordered pairs is root 2 over 2, comma pi over 4. And then if we're plugging in 3 pi over 4, cosine of 3 pi over 4 is equal to negative root 2 over 2. So we're going to have negative root 2 over 2, comma 3 pi over 4. I'll sketch this. Ooh, that was weird. I'll sketch this in a little bit to see what those points look like. But for now, let's leave those points right there. We've got two ordered pairs where we have horizontal tangents. Let's talk vertical tangents to wrap this up. So for vertical tangents, we want dx d theta equal to 0. So if we want dx d theta, we need to know what x is. We are going to start with x equals r cosine theta. And again, we were given what r is for this problem that we're working on. So we're going to take our r, we're going to substitute it in, and that is going to give us x equals cosine theta times cosine theta, or might make sense to write that as cosine squared theta. So if we want dx d theta, we now have a function of x in terms of theta, and we don't have to, again, think about all this wacky stuff up here at the top of our page. Now we're just taking the derivative of this thing with respect to theta. So this is chain rule this time, not product rule. So we have to take the derivative of the power first. That's going to be 2 cosine theta times the derivative of the inside, which is negative sine theta, which we might want to rewrite as negative 2 sine theta cosine theta. Another formula that maybe you recognize. We're setting this equal to 0 again, so if we can simplify this, it makes our life easier. So if you do note that this is actually equal to negative sine of 2 theta, it might make the solving a little simpler here. So if we want dx d theta to equal 0, we're going to do negative sine of 2 theta set equal to 0. So that is going to be when 2 theta is equal to 0, or pi, dividing by 2, you will see that our theta is equal to 0, pi over 2. And then we need some points again. So if we plug these angles into r equals cosine theta, that will be able to give us our r comma thetas. If we plug in 0, we get r equals 1. So that's the point 1 comma 0. If we plug in pi over 2, r is going to be 0. So those are our two locations where we have vertical tangent lines. So in a sketch, if you wanted to kind of see what that looks like, if you recall what r equals cosine theta looks like from the first part of our notes, it is going to be this circle over here on the right. That point right there is at 1. So at the point 1 comma 0, it is pretty easy to see that we have a vertical tangent. And at 0 comma pi over 2 over here, I think it's pretty easy to see we have this other vertical tangent. For our point root 2 over 2 comma pi over 4, it's actually up here at the top. Remember, it only takes pi to get around this whole circle, so pi over 4 is actually a quarter of the way around the circle. You'll see our horizontal tangent right there. And if we wanted to draw that a little bit, like to figure out where pi over 4 is, you know, we think about that line, kind of y equals x, that goes right there. That's where theta equals pi over 4 is. Hits the circle right there. And then finally, where is negative root 2 over 2 3 pi over 4. So 3 pi over 4 is somewhere over here. And since we're going out a negative radius, it actually sends it away from that 3 pi over 4 up there in the top left corner, so it actually sends it down there. And you can see that that is the place where we have the other horizontal tangent line. Okay, hopefully this was helpful. Please make sure you're trying your homework. When I get back tomorrow, we are going to start integration.